So we're going to evaluate exponential functions and modeling exponential growth and decay. So we're learning to solve problems involving exponential growth when we're given a formula. Okay? We're also learning to use the general formula for exponential growth, super important. So there's our exponential growth formula. We'll always be using, okay, to solve exponential growth problems. And we're learning to solve exponential decay problems, but we're just going to focus specifically on half-life problems. Okay? All right, so an investment of $1,000 grows according to the model A at t equals 1,000 times 1.08 to the power of t, where t is the number of years. How much is the investment worth after 5 years? So if you notice, the only variables are the amount and the time. Which one are we given? The time, 5 years, and we're trying to find A at 5, the amount at 5 years. Okay, so I'd probably just copy the formula down first. To the t. And then I find that amount at 5 years by substituting 5 in. Amount at 5 years is 1,000 times 1.08 to the power of 5. And then you got to be able to get that on your calculator. So most calculators you can type in 1,000 times 1.08 to the power of 5 and it will work for you. You should get $1,469, and if you round to 33 cents, it's the amount of money, so you round to dollars and cents. How much is the investment worth after 5 years? $1,469.33. So therefore, it will take, sorry, I'm reading the next question. Therefore, it will be worth $1,469.33. Okay? All right, how long will it take the investment to double? So again, you know we're starting off with $1,000. It's growing according to this exponential function. We know it's exponential because the variable is in the exponent. Okay? T is the number of years. How long will it take the investment to double? So what is that actually giving me? T or A at t? And which one of those do we know and what is it? It's A at t. Good. And what is it now? $2,000. Okay, so the amount of money, the investment is doubling, so it's going from $1,000 to $2,000. Does everyone see that? Okay, and we want to know how long does that take? How long is it going to take to get from $1,000 to $2,000? So again, we're going to copy down the formula. So this time we're replacing A at t with 2,000. And we're trying to get t by itself. So based on what we've learned when we solved exponential equations is that we always want the exponential part by itself. So to get that exponential part by itself, what would I do to both sides? Divide by 1,000? Yeah. So now I've got that 2 is 1.08 to some exponent. Now this is where it's not going to be exact. You're just going to have to use your calculator and trial and error to get as close as you can. So what you want to do is you want to write 2 as 1.08 as to the something. Because again, to solve an exponential equation, you want the same base on both sides. Okay? So what you're trying to do with your calculator is figure out what number you can put in that box there so that if the bases are equal, the exponents are equal. But you want 1.08 to the something to be 2. Okay? So I'd start off like to the 10. 1.08 to the 10. Does everyone see that's 2.15? So it's a bit big, so then I try to the 9th. 1.08 to the 9th. Oh, that's really good, right? That's as close as we're going to get. Next year when you learn logarithms, if you take advanced functions, you'll learn how to get it exactly to however many decimal points you want. But for grade 11, we just want to get as close as we possibly can. So we're going to put an approximate sign here because it's not perfect, but we got 9 is pretty close. Okay? So now that our bases are the same, our exponents are approximately the same, therefore t is approximately 9. So therefore it takes approximately 9 years for the investment to double. So therefore, it takes approximately 9 years for the investment to double. So the big thing here, which is unusual, it doesn't feel good, is I have to write 2 as 1.08 to something. So I'm only going to be able to get the answer close or approximately. I'm not going to be able to get it exactly until you learn logarithms in grade 12, and then you'll be able to solve it exactly. All right, exponential functions can be used to model many real-life phenomena such as cell growth, compound interest, radioactive decay, the spread of viruses, etc. Okay, so here's this would be growth. And usually when we're talking about a real-life situation, this is usually time down here. And we don't look at this part of the curve, really, okay? So our initial value will depend on what our vertical stretch, our A value is out in front. And then this is the part we focus on, the part of the curve where time is positive, okay? And same with exponential decay. Again, usually this is based on having time on the horizontal axis, so we just don't really bother with negative time, and then we have some initial value, and then we get smaller and smaller exponentially. Okay? All right, and then growth occurs when the base is greater than 1, okay? And decay occurs when the base is between 0 and 1, like a half or a third or a quarter, okay? And we know that from our parent functions yesterday. When we had parent function y equals 2 to the x, it looked like this. But when we had a half to the x, it looked more like that. Okay? All right, the exponential function f at x equals a times b to the x can model exponential growth. So here's the different pieces you need to know. F at x is the amount after x growth periods. Okay? A is the initial amount. B is the growth factor, so it's the base of the exponent. If you're doubling, it would be a 2, because you double every growth period. If you're tripling, it would be 3, because you're tripling every growth period. What if you're going up by 8%? What would B be? Increasing by 8% every growth period. Anybody? Okay, we'll get to that. And X is the number of growth periods, and there's a little formula for X that I like to use because I make sure that I've got it right. The total time divided by the time for one growth period. Okay? So those are the 4 parts of the formula. So we'll start off with a question that we use this formula pretty exactly. A bacterial cell culture initially has 200 cells. Every half hour, the size of the culture doubles. How many cells will be in the culture after 3 hours? All right, so given's like a huge part of this here. Do we know any of these 4 things, or do you have the information to find any of them?
You have the initial amount.
Yes. Perfect. Any other things we know? The growth factor, so B is, because we're doubling, B is 2. Can we calculate X, the number of growth periods? Yes. So what's the total time? 3 hours. And what's the time for one doubling? So 0.5 hours, which makes X equal to 6. Good. So we're going to start off with writing out our general formula. F of X equals A times B to the power of X. And then we're going to substitute in everything we know from our given side. So F at X is 6 equals A, which is 200, times, so bracket, 2 to the 6. And then we work that out on our calculator. So 200 times 2 to the power of 6 is 12,800. Make sure you can get that number on your calculator. I should probably put the 6 on the inside of the brackets, just so there's no confusion about it's 2 to the 6 times 200, not 200 times 2 all to the 6. And then we need a good therefore statement. So how many cells will be in the culture after 3 hours? Therefore, 12,800 cells will be in the culture after 3 hours. Okay. A bacterial culture initially has 1,000 cells. Every 2 hours, the size of the culture doubles. A, make a function to relate the number of cells n at t to the time in hours. Okay, so we're still going to start off with our givens, things we know. So out of the information from the question, what can you pick out that we know? No. A is 1,000. Good. What else do we know? B, every 2 hours, the size of the culture doubles. So this doubles tells me that B is 2. And X is the total time, which we don't know, so I'm going to call it T for total time, divided by the time for one growth period. So what's the time for one growth period? 2 hours. So X, I can change X to T over 2, where T represents total time. Again. All right, because it wants me to make a function. So I'm going to start off with my regular function, and then I'm going to change it over with the values that I'm given. So they want me to call my function n at t, number of cells at time t. So instead of f at x, I'm changing it to n at t. Equals, my a value is 1,000, so I'll put that in, times e to the x, so 2 to the power of t over 2. So there's my new function. So I'm done A. Make a function to relate the number of cells n at t to the time in hours. Done. Okay? Still an exponential function. It's just got more information in it. Right? It's got all my initial value, my base, and the time for one growth period. Okay, so B, how many cells are present after 3 hours? So it's giving me the time 3 hours. So it wants me to find the number of cells at 3, or n at 3. Okay? So n at 3 is equal to 1,000 times 2 to the 3 over 2. And you can type that into your calculator right away if you want, or you can change the 3 over 2 to 1.5 and then put it in your calculator. It's up to you just how good you are using your calculator. So 1,000 times 2 to the power of 1.5 is approximately, so we'll round to the nearest cell, 2,828. So therefore, after 3 hours, there are approximately, I'm going to use just approx with a dot, approximately 2,828 cells. And then C, how long will it take for 32,000 cells to be present? So again, we've got our formula, number of cells at time t is equal to 1,000 times 2 to the t over 2. And the question is, how long will it take for 32,000 cells to be present? So are they giving me a t or a number at t? Number, so I'm replacing n at t with 32,000. And I'm trying to solve for t, which is in the exponent. And anytime you're trying to solve for something in the exponent, you only want the exponential part left on the one side. So what would I do first? Divide by 1,000 on both sides. So that gives me 32 is equal to 2 to the power of t over 2. Which means I have an exponential equation to solve. Which means I need the same base on both sides. So I've got a base of 2 on this side. I have to rewrite 32 as 2 to the something in order to solve it. Need to have the same base on both sides. Yep. Yeah, so sometimes we're lucky and 32 is exactly, I don't need an approximate sign there. 32 is exactly 2 to the power of 5. Okay? So now that I have the same bases on both sides, therefore 5 is equal to t over 2, but I don't want t over 2, I want t, the total time. So how would I get t by itself there? Times both sides. Yes, times both sides by 2. So I get T is 10, and then what are the units of time? Hours. So therefore, it would take 10 hours for 32,000 cells to be present. Okay, the population of the town has grown by 8% per year since 1996. If there were 35,000 people in 1996, make a function for the population of the town, P at T in thousands, T years after 1996. Okay. Work on A here. So what things are we given? Remember, we're always thinking of this as our original equation and then changing it over. So you know A, B, yep.
A is 35,000.
A is 35,000. So that's our initial number of people. Nothing. B. Yep.
1.0.
Very good. How did you know that, Coleman?
35,000 tax on stuff. 1.13.
Okay, good. So sales tax, if you want to increase by 15%, you multiply by 1.15. Okay, that increases once by 15%. If you want to increase by 8%, then you would multiply by 1.08. Okay? A lot of people think you'd multiply by 0.08, but that decreases something. If you take a number and multiply by 0.08, it makes it smaller. In order to make it bigger, you have to multiply by 1.08. Okay, so remember that for percentage increase. And our X is going to be total time, which is T divided by the time for one growth rate, which is 1 year. So T over 1 is luckily just T. Okay? Total time over time for one growth period. Time for one growth period is 1 year. T over 1 is T. So we're ready to change over our general formula into a specific one for this question. So we're going to change f at x to p at t. A is 35,000 for this town. B is 1.08 for this town. And x is t for this town. So p at t is equal to 35,000 times 1.08 to the power of t. So that's A. B, use your function to predict the number of people in the town in 2012. Okay, so T is since 1996. So if I got to do 2012 minus 1996, that gives me how many years? 16 years. So T is 16. So I'm finding the population in the town after 16 years. He had 16. Is equal to 35,000 times 1.08 to the power of 16. And you get, after 16 years, the town's population is approximately, you get 119,908. Approximately 119,000 makes sense down to the nearest person, 908. Oops. So we need a therefore for that one. Use your function to predict the number of people. So therefore, the predicted population in 2016 is, sorry?
2012.
2012, thank you. 2012 is 119,908. All right, so that is B done. C is when will the population of the town surpass 75,000 people? So we know it's before 16 years, okay? Because we've gone way past 75,000 in 16 years. I haven't been screen yet. So we'll start off with our formula we made. And we want to know the time, which is in the exponent, it takes for population to reach 75,000 people. So we would want to get the exponential part by itself first. So what would we do to both sides? Divide by 35,000. Good. So that's going to give me an approximate. So I'm already going into my approximately dot zone here. So 2.14285.7 is approximately 1.08 to the t. And then we need the same base on both sides. So we need to write this number as 1.08 to some power. So I'm going to put in this box here. And then need the same base on both sides, so I can set the exponents equal to each other. So I got my calculator. I know it's less than 16. Is everybody good with that? So I might try 10, 1.08 to the power of 10. 2.15, so I'm going to try 9. Nope, 10 was closer. Everyone good with that? So it is approximate. We're not going to get exact here. Approximately 10. So T is approximately 10. But that's a number of years since 1996. So that means 2006. 10 years after, so 1996 plus 10 is 2006. So therefore, in 2006, the town will likely, instead of approximately, surpass 75,000 people. Number 4, a population of mice triple their numbers every 3 months. If there are initially 12 mice, how many will there be after 2 years? So again, we're always coming back to this formula for growth. Anything you can pick out from the question. A is what? 12. We start off with 12 mice. Good. He is 3. Why is it 3? We're tripling the number of mice. weeks each month. And then X is the total time, remember, divided for the time for one growth period. For one growth, I'll put. So what's the total time? 2 years, but we've got months and years, so we have to pick one, right? So if the total time's 2 years, I can't have years and months. I have to change them either both to months or both to years. Which one's easier to do? Right, so there's 12 months in a year, so the total time is 24 months. And the time for one growth period is 3 months. Which means X is going to turn out to be 8. Okay? So this formula is really important to remember. All right, so I'm going to start off with my general formula, and then I'm going to substitute in everything that we put on our given list. So X turns out to be 8, so I'm finding F at 8. So after 8 growth periods, there's going to be 12 times 3 to the 8th mice. Okay? After 8 growth periods, which is 2 years, there's going to be 12 times 3 to the power of 8 mice. So let's see how many there are. 78,732 mice. So therefore, there will be 78,732 mice after 3 years. 2 years, thank you. After 2 years. Okay, that's kind of the classic exponential growth problem from high school, okay? Yeah, they're doubling or tripling, and then how many will there be after a certain amount of time. A pot of water is heated on a hot plate. The temperature T in degrees Celsius of the water is a function of the time T in minutes since the hot plate was turned on. Okay, so you got a pot of water on a hot plate. Starts off at room temperature probably, then you turn on the hot plate and it starts to get hotter and hotter. Okay? The exponential function that models the water is given by that. So temperature at time t is equal to 21 times 1.3 to the exponent t over 2. And then why would they add on this restriction? What do you think? Where time is between 0 and 13 minutes.
How long it started from? Like it was
So it started at 0. Why do they only want you to go to 13? It start boiling or something like that. So after it starts boiling, this isn't valid anymore. Okay, something like that. Okay, so it's only valid for times between 0 and 13 minutes. Okay. All right, so A says, what is the initial temperature of the water? So there's kind of 2 ways you could answer this question. One is based off, we just know the structure of the formula, what the initial amount is, right? And if you just go with the structure of the formula, what do you think the initial amount is with our prediction? 21, because that's where it is right there. So our prediction would be 21 degrees Celsius, right? Would be the initial value. But you could also do that by finding t at 0, and you could also get 21 that exact same way. Because if you type that into your calculator, any number to the 0 gives you 1. 1 times 21 is also 21. Okay, so what is the initial temperature of the water? Therefore, initial temperature of water is 21 degrees Celsius. Okay, and if you know that it's 21 because you know the structure of the formula, then you don't have to show any calculation. You can just write down what it is. All right, B. How hot is the water after 10 minutes? Any idea how I would calculate that? Find out how hot the water is after 10 minutes. The little t, right? So t at 10 minutes is equal to 21 times 1.3 to the 10 over 2, which is 5. And then you put that in your calculator and see how hot the water's got at 10 minutes. Yeah, approximately 78 degrees Celsius. So therefore, the water is 78 degrees Celsius after 10 minutes. How long does it take for the water to boil? So you have to know that water boils at a temperature of 100 degrees Celsius. So that's our clue. It doesn't say specifically, but we kind of have to know that water boils at 100 degrees Celsius. Okay? And then we've got our formula. T at T equals 21 times 1.3 to the T over 2. And we could replace temperature with 100. And then you want to get the exponential part, so this part here by itself, so you're going to have to divide both sides by 2.
Yeah, why is it 21?
21, sorry, because I didn't write the 1 down. Thanks, guys. All right, so 100 divided by 21, that's going to probably be approximate here. Yeah, so 4.7619 is approximately equal to 1.3 to the T over 2. So now I want to get the same base on both sides. So I want to rewrite 4.7619 as 1.3 to the something. Okay? You need to have the same base on both sides. So you're going to try it out on your calculator right now. So 1.3, and we know it has to be between 0 and 13. That kind of makes it easier having that restriction, right? And we know it's bigger than 10. So 1.3 to the 13th, I'm going to try right off the bat. Oh no, that's T over 2, my bad. So that's not big enough. 1.3 to the 18 is too big. $17 was too small. Yep.
Oh, never mind. Same thing. It's too small now. 4 way on.
So I'm going to go to the 17.5.
I got 6.
I only
got 2.
Oh, we still got 6.
Oh, what am I was looking for 100. Okay, you guys got 6?
We got
1.3 to the 6. 4.8. Yes, that's good. I'm sorry, guys.
Well, we're going high.
My bad. Okay, so then we have our therefore. Therefore, 6 is approximately T over 2. But then we want T by itself, so we have to multiply both sides by 2. So 12 is approximately T. And then we have to make a sentence. So therefore, the water will boil at approximately 12 minutes. Okay, so those are our growth questions. We're only going to do one kind of decay question, and that is half-life. Okay. An important application of exponential decay has to do with radioactive elements. So radioactive elements decay over time, and the half-life of a radioactive element is the amount of time it takes for the element to decay to half of its original amount. So you started off with 50, how long does it take to get to 25 is that half-life, okay? Half-life is unique to the specific element. The formula scientists use to describe exponential decay, where half-life is involved, is A at t equals A sub 0 times 2 to the negative t over h. It looks like a complicated formula, but it's not that bad. So the meaning of the pieces are A at t is the amount left at time t, because we're always going to be decreasing, all right? A, that's a subscript, so that's written as A with a little subscript of 0, so it's the same size as an exponent, only it's lower case, or it's a little bit below. It's the initial amount of the substance. H is the half-life of the substance in the exponent. T is the total time, and it must be the same units as half-life. Okay, so these two have to have the same units. And if not, you have to convert. Anyone want to tell me why the exponent is negative? Yeah, so if my base is 2, if I had a positive exponent, I'd be getting bigger, right? But if I have a negative exponent, it's really making that 2 1 over 2, okay? It's just easier to calculate instead of typing a half in. You can type 2 in and use a negative exponent on the calculator. Okay? All right, good call. So here's a typical half-life question. A 320 milligram sample of iodine 131 is stored in a lab for 40 days. If the half-life of iodine 131 is 8 days, how much of the sample will remain? Okay, so out of those 4 things in the formula, which ones do we know from the question?
H is 8 days.
H is 8 days. What's another one we know?
T is 40.
T is 40 days. Another one that we know. A sub 0 is 320 milligrams. And that looks like an approximate, but it's just a mark by my smart pen here. All right, so now we can start off with our general formula and then substitute in. So A of t is A sub 0 times 2 to the negative t over h. So one thing I noticed students forget to do is they keep that as A at t, but once we're subbing the numbers in, it changes to A at 40. We're finding the amount at 40 days. So make sure that you do that. Change the t over to 40. So it says I'm finding the amount at 40 days. And it's going to be 320 times 2 to the exponent, negative 40 over 8. And you could go right to your calculator at that time, depending on how comfortable you are, or you can find that negative 40 over 8 to be negative 5 if you want as well. But as long as you use your calculator correctly, it doesn't matter. So when you type it in, you should get 10, exactly. Okay, so A of 40 is exactly 10. So how much of the sample will remain? Therefore, 10 milligrams of the sample will remain. After 40 days. Okay, number 7, a sample of plutonium-239 is allowed to decay. If the half-life of plutonium-239 is 24 years, how long will it take until 5% of the sample remains? A little bit of a stinker here. What things do we know? We can pick out right away. H is 24 years. What is it we're trying to find? T? That's our question mark. Any ideas how we could do this? This is the formula. What is knowing that the original amount decays to 5%, so there's only 5% left? Help us. Yep.
Because it means A at 0 would be 100%.
Yes. Okay. So do you want to do that? Do you want to say A at 0 is 100? Because we're dealing with percents here. A sub 0 is 100. I'm going to show you 2 ways to do it, okay? And then you can pick away. So we could do that. So if A at 0 is 100, what is A at T then? 5. Because 5% of 100 is 5. All right, so then if we substitute those things into our formula, we're going to get 5 equals 100 times 2 to the negative t, that's what we're trying to find, over h, which is 24. So then we would divide both sides by 100. Good. And we would get 0.05 equals 2 to the negative t over 24. And then we would have to write 0.05 as 2 to the something. Is everybody good? Two to the something. So remember, guys, like if we go bigger, like 2 to the 1 even is 2, 2 to the 2 is 4, 2 to the 0 is 1, 2 to the negative 1 is 1/2, which is 0.5. So we're looking at a negative exponent. Do you guys agree? When we're trying stuff out on our calculator, we're not going to be trying out like 1, 2, 3, 4, 5. We're going to be trying out negative exponents. 2 to the negative 2 is 1/4, which is 0.25. So we're looking at smaller than negative 2 even. Okay? So start trying stuff out, but negative exponents. 2 to the negative 3. Nope. 2 to the negative 4. Closer. 2 to the negative 5. So it's between 2 to the negative 4 and 2 to the negative 5. You might try 2 to the negative 4.5 and see what that is. Still a bit small. 2 to the negative 4.6. Well, that's even smaller, so I want to go 2 to the negative 4.4. 2 to the negative 4.3. That's good. That's as good as we're going to get, okay? And that's approximate. So therefore, negative 4.3 is approximately equal to negative t divided by 24. And then, what's a smart number to multiply both sides by? To get t by itself all in one step. Negative 24, good. Because that takes care of the negative and the 24. So positive t is approximately 103.2, and what's our units of time? Years? So therefore, it would take approximately 103.2 years for the sample to decay to 5% of its original amount. Okay, remember I said I was going to show you another way. You don't have to copy this down, but I'm just going to show it to you. Okay, so an alternative strategy is going to get you to the exact same answer. But that's to say that the final amount is 0.05 or 5% of the original amount. Okay, so it doesn't matter what the original amount is. I'm going to end up with 5% of the original amount, which means multiplying the original amount by 0.05. Okay? Now when I divide away the original amount, I'm left with this exact same equation, 0.05 equals 2 times negative t, sorry, 2 to the power of negative t over 24. Okay, and from here on, it's the exact same question, so just a different strategy. Okay, so it doesn't matter which way makes more sense in your mind. Okay, both good ways to do it. Carbon dating is a way for scientists to estimate the age of ancient artifacts. Carbon-14 has a very large half-life of 5,730 years. That's why they use carbon-14 to date stuff. Okay? A piece of fossilized wood was analyzed, and it was estimated that the original amount of carbon-14 in the piece of its size would be 8.5 grams. The fossil contains 0.7 grams today, 7.5 grams today, sorry. How old is the fossil? So what things can we pick out of the question that were given? A sub 0, so the amount that we started with is 8.5 grams. Another piece of info we can pick out from the question.
H or half-life?
Of the half-life, H is, yep. So the half-life for carbon-14 is 5,730 years.
You also have
T, yes, the amount remaining is 0.75 grams. And what are they asking me to find? Time. How old is that artifact or fossil? Okay, so we'd start off with our formula, our general formula for half-life. So A at t is A sub 0 times 2 to the exponent negative t over h. And then we'll put in all the values that Jarius told us. So A at t changes to 0.75. The original amount, 8.5. Times 2 to the negative t over 5,730. So what would I do to both sides? Good, we're getting the hang of this, which is awesome. So 0.75 divided by 8.5 is 0.088. 235 is approximately 2 to the negative t over 5,730. So then we want to write this side as 2 to something is approximately 2 to the negative t over 5,730. And because it's less than 1, we know our exponent's going to be negative, okay? So 2 to the negative 4.06, 2 to the negative 3, so it's between those two. To the negative 3.5, I got 0.088. Did you guys get that?
Yeah.
Yeah, that's close enough. So therefore, negative 3.5 is approximately negative t over 5,730. And what would be a smart number to multiply both sides by? Negative 5,730. Which would lead us to t being approximately 20,055 years. So therefore, the fossil is approximately 20,055 years old. And 9, I'm going to let you guys try on your own. Oops. Okay. So we know that the half-life of carbon-14 is 5,730 years. And then a lot of you put that the total amount was 37, and the original amount was 100, and then some people did the other way, which is fine. And time is what we're trying to find. Okay? And you would copy down your formula. So 37 equals 100 times 2 to the negative t over 5,730. Divide both sides by 100. Or if you did it the other way, divide both sides by a sub 0. You get 0.37 equals 2 to the negative t over 5,730. And now we're at the step where we have to write 0.37 as 2 to some number. It's probably going to be approximate. So now we go to our calculator. Lots of people were doing. I guess 0.37 is 2 to the something. Negative 1.4? Yes? Okay. So 2 to the negative 1.4 is approximately 2 to the negative t over 5,730. So negative 1.4 is approximately negative t over 5,730. Multiply both sides by negative 5,730. And we get t is approximately 8,064 years.
Yeah, 8,000.
I must have typed it in wrong. Yeah, I did. 730, not 760. 8,022 years. So therefore, what was it? Bison bone? The bison bone is approximately 8,022 years old. Okay. Everybody got it? All right, so I'm gonna stop.